Hello dear students, welcome to Pen and Paper Chemistry on YouTube.
Hello dear students, welcome back subscribers to Thermodynamics part 14. Here we shall be introducing the second law of thermodynamics and also be talking about a new thermodynamic term what we call as entropy. We shall be defining it, we shall be dealing with it vis-a-vis our daily life, and we shall also be talking about it chemically, or what you say more appropriately as thermodynamics. Before we start with this topic, we need to fill air into this balloon. Now, in order to fill air into this balloon, what are the various methods that I can use? Yeah, I'll either use a pump or I will use my mouth to blow it, right? So this is how we can inflate a balloon. As simple as that, right? Now, can this balloon inflate itself without air being blown into it? Can it be inflated? Yeah, very simple. We can't. We need some form of pump in order to blow air into it. Now let's suppose I make a small hole into it where, it bursts. So let's try and make a small hole into this balloon. I've got another inflated balloon, and with the help of a pin, I will carefully pierce it in order to make a small hole. Now, when we make a small hole into this balloon, what will you observe? What happens to the air inside the balloon? Yes, it will start escaping from it. Now, in order for the air to escape out of this balloon, do we need a pump? Is there any pressure required, or will it happen on its own? Go ahead. Yes, it will just happen on its own. So if you see, the air will start escaping from this balloon. You can hear the sound of the air escaping from this balloon, and you will also be able to see the balloon getting deflated on its own. So we've taken the same thing, we've taken a balloon and we have seen two things. Air being filled into the balloon and air coming out of the balloon. Air being filled into the balloon doesn't happen on its own. We need some external agency in order to carry out that process. Whereas air coming out of this balloon is a process which is happening on its own. Take another daily life example. You are sitting in a class. There is no teacher in the class. What will the students be doing in the class when there is no teacher? Be honest with yourself. I'm sure you'll not be studying and sitting in one place. You would be going all over the place and talking and making some noise, right? So that is something which comes spontaneously. On the other hand, if there's a teacher or if there is an exam, then in that case, what will happen is you will be doing your studies and most of you will be sitting in one place and doing your work, but not all of you. So there are some things which happen spontaneously. There are some things which need an external agency to do that. So we have classified these type of processes as spontaneous, non-spontaneous. A process which takes place on its own or by initiation, like in order to get the air out of this balloon, I had to pierce a small hole into it, right? So a process which takes place on its own or by initiation is what is called as a spontaneous process. A process, on the other hand, which requires a continuous input from some external agency is what we call as a non-spontaneous process. Another very common example. When ice melts, it's a spontaneous process. Water falls on the floor. After some time, there's no water on the floor. It just vaporizes. Those are examples of spontaneous process. On the other hand, if you leave water on the floor, will it freeze on its own? No, it doesn't, right? So it needs an external agency. You need to put it in the refrigerator for it to freeze. So it's an example of a non-spontaneous process. Thermodynamics second law introduces concepts about spontaneity and non-spontaneity. What does it say is, it's a very simple statement of something which we observe daily. All naturally occurring processes are spontaneous and thermodynamically irreversible. That means you can't inflate this balloon on its own unless you use a pump to do it. These are 5 different forms of the same law. We have stated it in 5 different ways. It is better that you know all the different ways in which the second law is stated so as to be able to correlate to what you are doing. But the context, the meaning, the state, what they mean is the same. For an irreversible process, entropy of the system and the surrounding increases, whereas for a reversible process, the entropy of the system and the surrounding remains constant. Now, if you see in this statement, I've talked about a new term, entropy. Reversible and irreversible we have already discussed in our previous videos. If you are confused, similarly system and surrounding also is there in thermodynamics part 1. If there is any confusion, I would request you to have a look at thermodynamics part 1 video in this series. We are talking about entropy in this. What is entropy? Entropy is nothing but chemical name for disorderliness, randomness, chaos. You are sitting in a class where there's a teacher in the class and you are having a regular class. See the second scenario, the bell rings for the snack break. What happens to the class? The whole class is jumbled up, people are going out, people are coming in, there's talking, so there is more chaos. So what has happened to the entropy? Has it increased? Has it remained the same? Yes, the entropy increases. So the second law says, for an irreversible process, entropy overall increases. I had this balloon. Air rushed out of this balloon when we pierced a hole into it, or when the balloon burst. In that case also the air just went out. It spread all over the place. It spread all over the surrounding. So the disorderliness or the randomness has increased. And those are examples of an irreversible process, right? How do we define it mathematically? We say change in entropy is given by the amount of heat change in the system. I'm using the word heat change because heat can either be absorbed or it can be evolved, divided by the absolute temperature. Absolute temperature is nothing but temperature in Kelvin. We are not talking about temperature in degrees Celsius. We're talking about temperature in Kelvin. That is why there is a capital T over here. What are the characteristics of entropy? It is an extensive property. That means more the number of children in the school, more the chaos. You have 10 children in the class and you have 60 children in the class. In which case is there more randomness? Yes, simple. So entropy is an extensive property. That means depending upon the mass of the substance that you have taken. Now, coming back to the mathematical expression, Q, heat, is expressed in joules in the SI system. Since it is an extensive property, I need to specify how much of the substance we are talking about. So entropy is heat, that is joule per mole, divided by the temperature, that is Kelvin. This gives us the unit of entropy as joule per mole per Kelvin. It's a state function. That means it does not depend on the path that you have taken to bring about that change. So whether it is isobaric, isochoric, it will not depend on that. It will just depend on the initial and the final state of the system. If you notice in this expression, delta S is inversely dependent on absolute temperature. In other words, if one increases, the other decreases. There is more disorderliness at lower temperature. This is low, this will be high. At lower temperature, the change in entropy on providing heat is much more than at higher temperature. So you can say that if you're already tired, you have had 2 hours of PE lessons and you come back to the class and still there is no teacher in the class, would that be more disordered or less disordered compared to when you have just been sitting in the class and been having your regular lessons? Yes, that's a simple anomaly that we are drawing, a simple comparison that we are drawing. So when you're already tired, when you already have had a lot of energy, when you're already high in temperature, then in that case, you will not, or more appropriately, when you're high in heat, then the change in entropy will not be so high as compared to when this is at low temperature. The change in entropy for any system or for any arrangement is always given by the entropy in the final state minus the entropy in the initial state. We shall be dealing more with this in the part 14 when we shall be talking about the various forms of entropy. Let us derive the mathematical expression for thermodynamics second law. Total change in entropy is given by the change in entropy of the system and the change in entropy of the surrounding. Now, change in entropy of the system will be given by Q system divided by T plus Q surrounding divided by T. We have taken 2 examples. Reversible isothermal process, where what happens is the amount of heat absorbed by the system is the same as the amount of heat lost by the system, by the surroundings. So if one is losing heat, the other is gaining. So delta S total is given by Q system divided by absolute temperature minus Q surrounding divided by temperature. Now just now we have said that the amount of heat change is the same, the physical quantity. One is the sign. If one is gaining, the other is losing. So plus and minus. The value of this heat absorbed or lost will be the same. In other words, my numerators become same at constant temperature. Hence, the total entropy of this becomes 0. That is why we say that for a reversible process or what we call as a process in equilibrium, the total entropy becomes equal to 0. A reversible process is one which takes place infinitesimally slowly so that there is always an equilibrium between the system and the surrounding. So at any stage it is possible for you to take the system back to its initial state. Come to irreversible process. Delta S total Q system divided by the temperature of the system, Q surrounding divided by the temperature of the surrounding. Now here you will notice that I have taken the temperatures differently. Why? Because we are talking about an irreversible process. For example, melting of ice. Now melting of ice will happen when does it happen? The outside temperature is more than the temperature of the system. Vaporization. Temperature of the surrounding is more than that of the water. So these are all spontaneous processes that we are talking about. That is why the temperature of the system and the temperature of the surrounding is different. Now here the temperature of the system is lower than the temperature of the surrounding when we are talking about these spontaneous processes. Therefore, now here your denominator is smaller. In other words, this whole expression becomes greater. So delta S total will be greater than 0 or it will be a positive value. So if you notice over here, for a reversible process or for a process in equilibrium or for a process in equilibrium, delta S total is equals to 0. On the other hand, for an irreversible or a spontaneous process, it is greater than 0. This we have stated mathematically as delta S of the system plus delta S of the surrounding is greater than or equal to 0 according to the second law of thermodynamics. So what we have over here is, what did the second law of thermodynamics say? For an irreversible process, entropy of the system and the surrounding increases. Whereas for a reversible process, it remains constant. We have three possibilities here. Delta S of the system plus delta S of the surroundings is greater than 0. So we said it's a spontaneous process. The summation of the two is equals to 0. It's a process in equilibrium. Delta S of the system plus delta S of the surroundings, if it is less than 0, then what? Yes, it's a non-spontaneous process. That means the process that I am talking about will not take place. What will take place is the reverse, the backward process, because in that case, delta S of the system plus delta S of the surroundings will become greater than 0 and the process will become spontaneous. The other forms of second law of thermodynamics, without the help of an external agent, spontaneous process cannot be reversed. Simple as that. If I've got a deflated balloon, I can't inflate it without the help of a pump. It is impossible to convert all heat to work without leaving some effect elsewhere. You need to understand this. We burn coal. Now, in the first law of thermodynamics, we said that energy is changing its form. Okay? I have this pen. Let's suppose this is on the ground. I pick it up, right? It is changing. The energy form is changing from kinetic to potential. Leave it, it will come down, potential to kinetic. Potential to kinetic is happening easily. Why isn't kinetic to potential happening on its own? So falling down is a spontaneous process, but coming up is a non-spontaneous process. Now, when I continue with this process, of course, there are other energy changes taking place as well. The chemical energy in my body, which is stored in the form of food, in the form of ATP, is being converted into the kinetic energy of the pen, then the potential energy, and then the kinetic energy. It is not that the whole energy that we are using is getting converted into useful work. Let's take another example. You burn a candle. That's nothing but a hydrocarbon. When you burn, you get carbon dioxide, you get water. As side products, the main purpose of you burning the candle is to get heat and light. So what is happening is, a candle on burning is giving you heat and light. At the same time, the energy is also getting converted into the chemical energy of carbon dioxide and water, which is of no use to you. It is just being added to the universe. It is just adding 2 more gas particles to the universe, right? So, it is ultimately increasing the entropy of the universe. Why am I saying increasing the entropy? If you compare the entropy of, let's say, the solid form of a substance, the liquid form of a substance, and the gaseous form of a substance. Entropy of solid, liquid, and gas. which will have highest entropy? Yes, the gaseous form, followed by the liquid, followed by the solid. In the gaseous form, the particles are far away from each other. In liquid, solid, they are closest. They are tightly bound with each other. They don't allow that freedom of space to each other. So they're, holding each other. On the other hand, in the case of liquids, they're providing some freedom. Okay, go on. But you can stay within the confines of this container. And the gas, they are all over the place if given the freedom to do so. So what we have is, we are ultimately adding to the randomness by burning this candle. So there is some form of energy which you are getting. Of course, there is interconversion of energy which is happening. But there is some form of energy which is not of any use to you. That means it is getting converted into non-usable form. So we don't call it exactly as wastage, but the energy has actually changed its form into some form which cannot be used by us. That is why we say it is impossible to convert all heat to work without leaving some effect elsewhere. If that was not the case, so supposing I had a system and the system is having energy E1, by one set of process, I take it to a stage where it has energy E2. So I have graph here. So I give it some amount of energy, increases the energy. I reduce the energy. Now in the whole process, now E1 to E2, when taking it, we need to do some work over here, right? E2 to E1. Again, that work will be lost, but which can be used in the first process again. So what is happening is, I am simply causing this change of energy, and at the same time, I am getting some work done out of it. In other words, this machine doesn't need anything from outside. It is self-sustaining, what we call as a perpetual motion machine, which practically we know is not possible. You burn fuel in your car. Is the fuel giving you the efficiency that it should? Are you getting 100% efficiency from that fuel? No. There's the exhaust, there's the smoke, there is the rubbing of the parts of the car, so there is wear and tear. So what is happening overall is, there is some form of energy which is getting converted into the non-usable form. Last, entropy of the universe is continuously increasing. If you see around you, what is happening is, because any process which is happening naturally is moving towards maximum randomness. The snow melts, flows down as water. The water evaporates, goes into steam. These are all naturally occurring processes, and these are taking place on their own, spontaneously. So we say entropy of the universe is continuously increasing. It is heading towards more and more randomness. So we had the first law of thermodynamics, which said that energy of the universe remains constant. We have the second law of thermodynamics, which says that entropy of the universe is continuously increasing. So let us combine the first and the second law of thermodynamics, and we have a combined statement which says that energy of the universe remains constant. It's just changing its form. That is not being denied, but it's changing into a form that is not so usable. While the entropy of the universe is increasing. This is what we call as the combined statement of the first and the second law of thermodynamics. we shall be talking more about entropy, and we shall be also doing some numericals questions based on entropy so as to make the concept clearer. You have any doubts, please feel free to leave your comments or ask your doubts. Also, if not done so, please subscribe to the channel Pen and Paper Chemistry. The whole content matter of this video has been also put on the Google site Learning Chemistry is Fun. I would request you to visit that site in case you want written notes on that. Happy studying to all of you. The only mission of this channel is to make learning chemistry easy and fun for all you students. With the help of the periodic table, the flowcharts, the graphs, diagrams, dealing with numericals, how to deal with numericals, and this can only happen when you keep a pen and notebook ready so that you can also take down notes for offline reference. There is no subscription to join the channel, there is no payment at all. Only request is to help spread a word about the channel by sharing it with friends, classmates, juniors, seniors, so that chemistry can be easy and fun for one and all. See you in the next video.